So let's do an example with the surface charge density. Let's say we have our sphere, a conductor, has a surface charge density of eta and a radius of r, big R. If we wanted to find the electric potential between any two points that were outside the sphere, we would need an equation for the electric field outside the sphere, which we've derived before using Gauss's law. E times the area of that imaginary surface we've drawn to include the point we're interested in, equals charge enclosed over epsilon naught. The charge enclosed would be eta times the surface area of the actual sphere, the actual charged object. So 4 pi big R squared. The 4 pi's cancel. So the electric field outside of our spherical conductor looks like that. Big R is the actual radius of the conductor itself. Little r is whatever point we're interested in, but little r has to be bigger than or equal to big R. If we want to know the potential difference between any two points out here, some r initial to some r final that's out here further, delta V is the negative integral of our electric field dotted with our displacement. As long as we're moving radially outwards or inwards, the electric field's parallel to the displacement, so that takes care of the dot product. Bless you. So delta V, the eta, the big R squared, and the epsilon naught are all constants. That leaves us with the integral of 1 over little r squared, which is negative 1 over r. Our negative signs cancel here. Delta V ends up being eta big R squared over r final times epsilon naught minus eta big R squared over r initial times epsilon naught. It gives us the difference in potential between those 2 points. It does not give us the potential at any point. If we want to know the potential at a given point, we need to know it, what the value is at some other point. For example, if we say our final, that final point we're getting to, is infinitely far away from this sphere, we would expect the potential final then to be 0. We would expect the potential infinitely far away to be 0. Delta V, remember, is V final minus V initial. So if V final is 0 and R final is infinity, that makes this term go to 0. That tells us that negative V initial is equal to negative eta big R squared over R initial epsilon naught. So basically V, the potential at any point outside of our sphere, is equal to this. Which, by the way, is the same thing as that. If you knew the actual total charge, because eta would be the total charge over the surface area, which would be 4 pi big R squared. Big R squared should cancel. It would give us 4 pi epsilon naught in the bottom. So 1 over 4 pi epsilon naught is k, q over r. This equation works everywhere from the surface out. It does not work inside. Someone started out a question.
Yes. They work on all these equations separately and then somehow they just magically...
I don't know. I don't know how the big how it all fell together.
Well, this is all based on Maxwell. Maxwell kind of.
Maxwell took all these little individual equations and pulled them together and played with them. So the individual equations were discovered before Maxwell came along. Whether they came up with this sort of thing first and worked back to the electric field or found the electric field and worked, I don't know.
Pretty cool coming from me.
Inside of our conductor, we're assuming our conductor is in equilibrium. That's why it has a surface charge density. The excess charge it contains is only on the outside surface. So what is the electric field inside of a conductor?
0.
0. Which, interestingly enough, if the electric field is 0, since delta V is directly related to electric field, then delta V has to be 0 as well. Now that doesn't mean the potential is 0 inside there. Remember, delta V is some V final point minus some V initial point. Your initial and final points have to be on the surface to inside. They can't be anywhere else. So little r has to be less than or equal to big R. We know the value of V at the surface. This equation for V worked at the surface working outwards. So at the surface, depends upon which equation you want to use. We're going to just put little r, big R in for little r, so we can write it in terms of eta, or we can write it in terms of total charge Q. So the surface of our conductor has a certain potential value. What this relationship tells us, since the electric field inside is 0, the difference between any point inside and another point inside is 0. So what can you tell me about the potential, say, here versus here?
They're both the same.
They're the same. This has the same potential value as this. The potential value inside, anywhere inside, is equal to the potential value at the surface. So everywhere inside the conductor, everywhere on the surface of the physical conductor, the potential value will be the same. It's actually a really important piece of information. That means any conductor that's connected in any way, so if I had two spheres connected by a wire, the charges would move around until the potential was the same everywhere. On the two spheres, on the wire, the potential would have the same value everywhere. The charges will move around until that occurs. That means if I have, say, a sphere with a total charge big Q and a big radius big R, and I had a smaller sphere of Q over little r, if I connect these up by some sort of conducting wire, of course, the charges are going to move around until V for this guy equals V for this guy. That's how the charges distribute themselves. So basically the ratio of KQ over big R ends up having to equal K little q over little r if they're in contact with each other. So any conductor in equilibrium has the same potential value everywhere. And we're going to use that as we start looking at circuits. And we're going to look at just a few basic circuit elements, nothing too deep and involved, but this will come